everyone, so for this problem we are going to evaluate 3 different series to see if they converge. For each series we will identify and explain what type of series it is and then go step by step evaluating for convergence. The first series is the sum of the terms of the sequence 1 over the square root of n from n equals 1 to infinity. This is a p series, which is represented by the notation the sum of the terms of the sequence 1 over n to the p from n equals 1 to infinity. In this p series, p is equal to 1/2. In general, for p series, when p is greater than 1, the series converges. This is because the terms are quickly approaching 0, so they are not too substantial in size. When p is less than or equal to 1, the series diverges. This is because the terms are too substantial in size to converge when they are added. Remember, when p equals 1, it is a special kind of series called a harmonic series. So in this problem, because p equals 1/2, which is less than 1, the p series, series 1, diverges. The second series is the sum of 3 to the n over n factorial from n equals 1 to infinity. So this is an infinite series, but it is not one of the special types of series that we have learned. It is not a p series because there is not an n to some value in the denominator. It is not a geometric series, which is represented by the sum of the terms of the sequence a times r to the n from n equals 0 to infinity. Some students may quickly look at the numerator and see the 3 to the n and assume it is a geometric series. However, with the n factorial in the denominator, it cannot be. It is not an alternating series, a series whose sequence is -1 to the n or n plus 1 times the general term a sub n, because the terms do not alternate in sign. It is not a power series, notated as the sum of the sequence of a sub n times x minus t to the n, because there is no x term. Since the series is not any of these special series, it is just an infinite series. Whenever there's a series with n factorial, it is best to use the ratio test to test for convergence. The ratio test says, for the series of a sub n where all terms are positive, let the limit as n approaches infinity of a sub n plus 1 over a sub n be L. If the limit is less than 1, the series converges. If the limit is greater than 1 or approaching infinity, the series diverges. If the limit equals 1, the test is inconclusive, which means that another test must be used to test for convergence. So for this problem, a sub n is 3 to the n over n factorial. For a sub n plus 1, you add 1 to all of the n values so that you have 3 to the n plus 1 over n plus 1 factorial. Before we evaluate the limit as n approaches infinity of a sub n plus 1 over a sub n, we should use ideas from algebra to expand both a sub n and a sub n plus 1 so that we can later simplify them. We can break up 3 to the n plus 1 into 3 to the n times 3. It is often forgotten we can do this, but think about how x squared times x to the 5th can equal x to the 7th. Also, we can turn n plus 1 factorial into n plus 1 times n factorial. This is a confusing concept, but here is an example showing how we can do this. For example, we know 5 factorial equals 5 times 4 times 3 times 2 times 1. So 5 factorial can also equal 5 times 4 factorial, which is 5 times 4 times 3 times 2 times 1. So now that we've simplified it, let's evaluate the limit. So we have the limit as n approaches infinity of 3 to the n times 3 over n plus 1 times n factorial. This is all over 3 to the n over n factorial. Remember that when dividing by a fraction by a fraction, we can multiply the fraction in the numerator by the reciprocal of the fraction in the denominator. So now that we have done this, we can start simplifying. We can simplify the 3 to the n's, the n factorials, and now we have the limit as n approaches infinity of 3 over n plus 1. When we plug in infinity, when you're dividing by infinity, you're approaching a very small number, which is practically 0. So the limit is 0. Because the limit equals 0, which is less than 1, by the ratio test, we know that series 2 converges. The third series is the sum of the terms of the sequence e over pi all to the n from n equals 1 to infinity. This series is a geometric series. A geometric series is represented by the sum of the terms of the sequence a times r to the n from n equals 0 to infinity. A is the coefficient and r is the common ratio. In a geometric series, the first term must be in the form of a times r to the 0. So if the series does not start with n equals 0, you have a problem. Because series 3 doesn't start with n equals 1, we can adjust the series so the first term will be raised to 0 by subtracting n by 1. So the sum of the terms of the sequence a times r to the n from n equals 0 to infinity equals the sum of the terms of the sequence a times r to the n minus 1 from n equals 1 to infinity. The most common error made for geometric series problems is failure to adjust the series when the first term doesn't start with n equals 0. First, we will split the common ratio e over pi into two parts by the numerator and the denominator. By splitting it up, it will make it easier to understand how algebraic properties allow us to put the series in terms of n minus 1. First, we will multiply e to the n by e over e. We can do this because e over e is 1, so we're allowed to multiply by 1. We can subtract the 1 exponent from the denominator of e over e so that we now have e times e to the n minus 1. If this seems confusing, remember, if you're multiplying two terms with the same base, you add the exponents. So if you were dividing two terms with the same base, you subtract the exponent of the numerator by the exponent of the denominator. For example, if you have x to the fifth over x squared, you can subtract 5 by 2, and you know you have x cubed. We will now do the same thing with 1 over pi to the n. Multiply it by pi over pi, which, like I said earlier, is 1. Subtract the n exponent by the 1 exponent in the numerator. So we have n minus 1. Now we have 1 over pi times 1 over pi to the n minus 1. We can multiply both of the components together. Now the coefficient is e over pi, and the common ratio is still e over pi, but now it is raised to the n minus 1. Now that the series is starting with the correct term, we can use the rules of convergence for a geometric series to evaluate series 3 for convergence. Note that the ratio did not have to split into two parts like we did. You probably noticed the new coefficient is just the same as the common ratio, but by doing it this way, you now have a better understanding of why this algebra was possible. For geometric series, if the absolute value of r is less than 1, then the series converges. If the absolute value of r is greater than or equal to 1, then the series diverges because the terms are too big to be adding infinitely many of them. Without using a calculator and our knowledge of the values of e and pi, we know that e over pi is approximately 2.718 over 3.14, which is less than 1, so the geometric series, series 3, converges.